Have you ever looked at a complex operational amplifier circuit and wondered how engineers quickly analyze its behavior without getting lost in intricate details? It often comes down to understanding a few key simplifying principles. The virtual short assumption for op-amps is a powerful simplification that states the voltage difference between the inverting input terminal and the non-inverting input terminal of an ideal operational amplifier is effectively zero. This means that if you know the voltage at one input, you immediately know the voltage at the other input, as if they were directly connected by a short circuit, even though no current actually flows between them. This assumption arises from two fundamental characteristics of an ideal operational amplifier: infinite open-loop gain and infinite input impedance. The infinite gain means that even a tiny voltage difference between the inputs would produce an enormous output voltage, which is typically constrained by the power supply. For the output to remain as finite and stable, the differential input voltage must therefore be driven to zero by negative feedback. The infinite input impedance ensures that no current flows into or out of the input terminals, so this virtual short does not actually conduct current. Understanding this virtual short concept is crucial for quickly deriving the gain equations of many common op-amp circuits, such as inverting, non-inverting, and differential amplifiers. For instance, in an inverting amplifier, since the non-inverting input is usually tied to ground, the virtual short implies the inverting input is also at ground potential. This simplifies the voltage division calculations significantly, allowing you to easily determine the output voltage based on the input signal and resistor values. This idealization, while a simplification, proves remarkably accurate for most practical applications because real op-amps typically have very high, though not infinite, open-loop gain and very high input impedance. This allows engineers to analyze and design stable feedback circuits with confidence, predicting their behavior with a high degree of precision. It is the cornerstone for understanding how negative feedback forces the input terminals to nearly identical potentials. Ultimately, the virtual short assumption acts as a critical shortcut in operational amplifier analysis, transforming seemingly complex feedback loops into straightforward voltage and current divider problems. It empowers you to efficiently determine circuit functionality, allowing for quick design iterations and effective troubleshooting, all by leveraging a simple yet profound ideal characteristic.